Good afternoon. I am Krishna Kumar from Krishna's classroom. We have completed the discussion on diagonalizable operators, and we have also seen some examples where diagonalization is not possible, and that opens the question: how do we handle non-diagonalizable operators? Because there exists non-diagonalizable operators. So how do we handle such operators? Is it still possible to get matrix representations which are simple in some sense and transparent in some sense? Although it may not be possible to get one as in the diagonalizable case, where you get a diagonal representation. Diagonal representation may not be possible, but still there could be some good transparent form in which we can get a representation for such operators. Now this is what we are up to. Okay, let us just recall a few facts about diagonalizable operators first, and then proceed to consider non-diagonalizable operators. So we first assume P belonging to LV is diagonalizable. Then the characteristic polynomial P is of the form f of lambda equal to lambda minus lambda 1 to the power n1 where lambda 1, lambda k are k distinct zeros of f with respective multiplicities So let G lambda defined by that means we are keeping the exponents to 1. That's the simple linear product. Then we found that if P is diagonalizable, then f of t equal to 0. That is f of t equal to t this is f of t, and f of t becomes the zero linear transformation. Okay, zero unit of solution. Further, g of t is also zero unit. Okay. Now this is the scenario that you have in the diagonalizable. You have both f of t equal to 0, g of t equal to 0. Okay. Now we have seen that if you have looked at the way in which we proved this, because t is diagonalizable, we said that W can be split up into WK, where Wi equal to null space of t minus lambda I, and we adds up for W1, W2, etc. Wk add up to cover the entire B. Now this is what happens. And W1 is the eigenspace associated with lambda 1, etc. Wk is the eigenspace associated with lambda k. And that is clear from this definition of Wi. Now you see that this means V can be written as W1 plus Wk uniquely, and each Wi is the eigenvector of T associated with the eigenvalue lambda I. So we have this property T of Wi now let us make use of this. Then we see that easily verify that all these factors are commuting factors. Okay, they do commute, so it is immaterial in which order you write this. Now that's the important thing. Okay, and one can easily show that g of t equal to 0. The reason being g of w1 is 0, g of w2 is 0, g of wk equal to 0 for different reasons. Because W1 is in the null space of T minus lambda 1 I, and therefore if you bring that factor, because it commutes, that factor can be brought closer to W1, and you see that immediately the action of T minus lambda 1, T minus lambda 1 I on W1 equal to 0. And therefore, if you multiply by the other factors, now that's equal to be, that's going to remain 0. Similarly, for all i's, this happens. And therefore, we have g of t equal to 0. Now, g divides f. Obvious. G divides f as polynomials. Therefore, you see that which implies f of t is also equal. Now, this much observations we make, right? But you see that if you carefully analyze what is going on, it is only because W1, W2, Wk are the eigenspaces associated with the lambda 1, lambda 2, etc., lambda k respectively, and V is the direct sum of W1, W2, etc., Wk, that we are able to push this argument across. Okay. Now let us see what happens if this does not happen. What is the consequence if this does not happen? So now we assume T is not diagonalizable. Let us look at some example. The first example is the one where we had B equal to P1R, and we have B, the ordered basis chosen as 1T, because it is the polynomials of degree less than or equal to 1, including 0. So this is the vector space that we have. Okay? And we define T1 to be equal to x, and T to Tx defined as minus. Therefore, you see that the representation for T with respect to B is given by 1 and minus 1, 0. That's the matrix representation with respect to T. Now you see that if f of lambda is then okay, that's a characteristic polynomial associated with TB, which is a characteristic polynomial associated with T, and that is given by lambda square plus 1. Now one quickly observes that Ft equal to, what is lambda square? T square plus I. What is T square? Now you observe that T1, so this is extended to the whole space. So we will see what is T square 1 equal to minus 1, because T1 is x, T square 1 is Tx, Tx is equal to minus 1, therefore this is equal to minus 1. Similarly, T square of x equal to T square x equal to minus 1, therefore, Tx is equal to minus 1, therefore T square x is equal to T of minus 1, that's equal to minus x. Okay. Therefore, you see that the matrix representation for T square is equal to minus 1, or T square is equal to minus 1. Which implies f of t equal to t square plus I, which is equal to minus I plus I, which is equal to 0. Therefore, we have f of t equal to 0. Now we know that in this specific case, As long as your vector space is P1R, this does not break down at all. Further, the polynomial does not break down further at all. So there are no real roots for the polynomial lambda square plus. Okay. However, we have seen that if V is taken as equal C, that means with complex coefficients, all polynomials of degree less than or equal to 1, P1C, all polynomials of degree less than or equal to 1 with the complex coefficients, and then we proceed in the same way. We observe that f lambda in this case it splits into linear factors and T is diagonalizable. In that case, T is diagonalizable. So in this case, what about f lambda equal to g lambda? Okay, and f lambda is ft is 0, so gt is also equal to 0 in this case, because in the case of P1R, G is not defined because it doesn't, F does not split into linear, the product of linear factors. Okay, so we make one observation that even if T is not diagonalizable, still f of t equal to 0. Now this is the important conclusion that we made. F of t equal to 0. And of course, in the diagonalizable case of P1C, g of t is defined, g of t equal to f of t, therefore both f of t equal to 0 and g of t. This is the special case, diagonalizable. So here t is diagonalizable. Because you can show that the actual splitting of V takes place. Okay. Anyway, the dimension of W1 plus W2 in this case is equal to 2, which is the dimension of each. Therefore, everything works well. Okay. So, what we have made this observation on this example. Now, let us take another example. The second example is more revealing. It gives better insight into the problem. So slowly we are trying to get better insight into the problem of non-diagonalizable or for handling non-diagonalizable operators. So let us take this example. This example we have considered earlier and we have done extensive analysis of this to some extent, but we have not completely explored the whole thing. Okay, so let us consider the example 2. Or I can put this as example 2 and this as example 3. We take V to be equal to V2R. And then we choose the ordered basis as 1x squared. Okay. Now we define T by fixing what t does on one, x and x square, and then extend it linearly to the whole space. So t1 equal to we set this as 3 plus 2x plus 2 square, tx equal to 1 plus minus x, and we have t of p where px is p naught p1x. This is what I mean by extending this by two linearity. So now t is well defined and belonging to this belongs to t. Okay. Now you see that, so let A denote t with respect to the order basis. Then t with respect to ordered base b, which is equal to A, is equal to the 3 by 3 matrix, 3, 2, 2, that's the first column, 1, 2, 2, and minus 1, and 0. That is 0. Now the characteristic polynomial is f lambda equal to lambda minus 1. That you can easily work out. This can be easily computed. Let's just a minus lambda I, determinant of a minus lambda I equal to 0. Complete the whole thing. Okay, right. That's the characteristic point. Now in this problem, something quite interesting happens. Now we see that if I define W1 as t minus 1i, 1 is the eigenvalue. Okay, W1 as the null space of then dimension of W1 is equal to 1. Okay. It's clear. Because you can show that the t minus lambda I or a minus 1i, if you take and look at the rank of that, the rank of that is going to be 2. Therefore, the nullity of that is equal to 1. Similarly, we can work out the nullity of t minus 2y. Let me see that the dimension of W2 is also equal to 1 in spite of the fact that lambda minus 2 appears in f lambda with exponent 2. That's the problem. It's not 1. Okay? Right? Therefore, a lot of interesting things happen. First of all, first thing that you observe is that B is not equal to okay, because the reason is V is not equal to W1 plus W2. Of course, W1 intersection W2 is consists only the zero vector, that is valid, but this is not true. And this implies we cannot projection operators P1 and P2 such that we cannot get equal to 5. This is not possible. Okay? So if you proceed as we did in the spectral theorem, define P1 and P2, then this fails to be equal to I. Okay? That is P2 not equal to I. Hence P is not diagonalizable. Well, let us check the status of Ft. And what about Gt here? By our definition of G, now G lambda is in this case lambda minus 1 into. Now we ask what happens to let us go through this computation. One can see that, see, we have the following computation. The eigenvectors of and 1 plus x plus 2x squared belonging to the eigenvalues 1 and 2 therefore we have in fact W1 is spanned by we have W1 equal to span of W2 is span of 1 plus x plus 2 x square. Both are one dimensional. That's the problem that we have seen. Okay. So we have P of 1 plus 2x square equal to 1 plus 2x square. P of 1 plus x plus 2x square. This is equal to 2 times you can easily verify this. Now we look at this. What is FT and GT? You see that this does not cover the entire V. There is some gap. You have a portion of a two-dimensional subspace of the three-dimensional space V covered by these two vectors. I mean, you know, these two vectors, if you use them as an ordered basis, you don't get enough vectors to cover the whole space coming out as eigenfunctions of T. That's the problem. Okay. Now we observe that f of t equal to 0 and g of t is not equal to 0. Let us quickly do some computations. Now you see that, see f of t equal to 0 if and only if f of a equal to 0. So we have to only compute. Now this is quite easy to see. Like, look at the relation between t and a. A is tb. Okay, so that's quite easy to, because it's something like you know, we have seen our figure that t operator is actually phi inverse at the end, so it's something like phi inverse t phi. This is equal to, well, phi is isomorphism between P2 and R3, subordinate to the choice of the order basis 1x x square. That's what. So you see that these are invertible maps, or these are isomorphisms preserving the structure. Therefore, you see that one can easily prove that compute this. F of a you can compute, f of t you can compute, then you see that f of t is essentially 0 if and only if f of a is 0. That's quite easy to work out. So let us compute this. So it's enough to compute f of a and g of a. Same story about g. Same story about g. Now let me compute this. So f of a we will compute. This is equal to and this you can compute, but before that we will have g of a now again if therefore f of a is equal to okay, let's now write down what they are. So a minus I, this is actually equal to 2, 1 minus 1, 2, 2. This is a minus I. This is equal to 1, 1 minus 1. 2, 0 minus 1, 2, 2 minus 2. So you already said what exactly A is, so it's easy to compute this. Okay. Now let us compute G. This is equal to multiplied by 1, 1 minus 1, 2, 0 minus 1, and 2, 2 minus 2, and that turns out to be 2 minus 1. This is what you get. And this is not equal to, this is not the zero matrix. Okay, so GA is not equal to 0. Consequently, so this is one observation that we make in this particular example. GT is not equal to 0. Similarly, now FT let us calculate. FA turns out to be GA, we already have, multiplied by P minus or A minus 2I. This is equal to GA, you already know what it is, we have computed it. This is 2, 0 minus 1, 2, 0 minus 1, 2, 0 minus 1 to be multiplied by A minus 2I. A minus 2I is 1 minus 1. And if you take the product, make this multiply this, you will get, that is the 0 units. Therefore, you have, although it is not diagonalizable, still f of t equal to 0. But g of t is not equal to 0. This is something that we should register in our mind. And at a later stage, we will recall this example again. We will have an analysis of this. Thus, we make the observation. The characteristic polynomial vanishes. Not diagonalizable. That means we cannot write that potential. F of t is equal to 0, but g of t is not equal. That's a very interesting information. You know that g is defined only in those cases. So remark, g is defined only those cases where f splits into products of linear factors. Linear okay. So this is something that we keep in mind. So wherever G is defined, see in the case of diagonalizable case, we have conclusively proved that both Ft equal to 0, Gt equal to 0. Okay, so T diagonalizable. So we will just recap what we observe here, and then so T diagonal implies equal to 0 for the characteristic polynomial. G of t is defined and G of t equal to t. This is one observation. Now in the examples, this we have conclusively proved. In the case of the examples, we consider T non-diagonalizable still Ft equal to 0, but Gt is not equal to 0. So F does not annihilate T. Let me use that word because we will bring that word into our our discussion soon. But G does not annihilate T. Okay. So this is the observation that we made. Still this is true, but Gt is not equal to T. So we have made some observations. There are a few facts. What are the facts? See, T diagonalizable means F splits into linear factors. Secondly, G is as defined in the corresponding case as the product of these linear factors with exponent 1. Then we observe that whenever t is diagonalizable, all these things happen. F of t equal to 0, g of t equal to 0. But in the examples that we considered, wherever t was non-diagonalizable, still we had ft equal to 0, but gt not equal to 0. gt may not be defined in some case as the way in which we have defined it, as we have seen in that simple case of v equal to p1, okay, where we found that the moment we went to the case of p1c, the operator was diagonalizable. In that case, we had both f and g identical in that case. In that case, f was 0, g was 0. In all the cases, we found that ft equal to 0. But in the non-diagonalizable case, we conspicuously observe that g, if it is defined, gt may not be 0. Now this is the observations that we make. And these observations later we will make use of in getting some clue or some cue to how we should develop a general theory. So the immediate question that comes to your mind is this. The question that comes to your mind is the following. Suppose T belongs to L with the basic conditions that we have assumed in the beginning. Is ft equal to 0 irrespective of whether T is diagonalizable not. Now that's a broad question that we are going to ask. In other words, what we want to assert possibly is that the characteristic polynomial annihilates T in the sense that if f lambda is the characteristic polynomial, f of t equal to the 0 linear operator. Okay? So that's the first question. Is this true for all linear transformations? After all, what we have done is just taken some examples and there we have just verified that these kind of things happen, and that is not an acceptable thing. It gives some insight into what could be right, but still we don't have a proof for that. So this is one of the questions that we consider. Okay. A second question is is there any way the structure of F suggesting diagonalizability? That is another question. Okay. some property of f and g possibly together tells you or that t is diagonalizable or not. Okay. Is it possible to characterize diagonalizability of T in terms of the structure of the characters. We have seen that the characteristic polynomial is something that comes out of T. Therefore, we need not be surprised that if there is some such indication from the structure of the characteristic polynomial, and we will be essentially looking for this kind of results. Okay. So now we make some further remarks. What are these WIs? See, in the case of diagonalizability, we have seen that we were computing WIs, which are the eigenspaces. And eigenspaces are invariant. In the case of diagonalizability, WIs are eigenspaces. And we also have T of or WI is an invariant subspace of T. So this is something that we observe for I belonging to with our standard notations. Therefore, we read between the lines and infer that the diagonalization, of course, after all, what were we doing? We were searching for the eigen vectors and then using them as an ordered basis for V. That means we were constructing essentially these WIs. So we are looking forward to determining invariant subspaces of V associated with the given T. Determining invariant subspace of. Let us see what happens to matrix representation if T has a invariant subspace. Taking the quite general case. So let us examine this. The scenario where non-trivial associated with T. So let us take, so we have B n dimension. That's the assumption. Let W be such that T of W is contained W, where W is a proper subspace of V. Assume dimension of W equal to K, where of course K is strictly less than. Under this situation, what we can do? What we can do is the following. We can construct a basis. So we can construct a basis of V as an extension of a basis for W. So let us compute this. Okay. Basis for W. We extend this by adjoining vectors Vk plus 1 Vn to it such that so this is what we have. This is V, this is W. The property that T has T W T maps every vector in W into itself. This is what T does. Okay. Whereas you do not know what happens to the rest of the space. But for all vectors of W, we know that this is true. Therefore, what do we have? We have, see, let us now find out what it does on V1, V2, etc. You know that T V1 is then and see, this is a linear combination of V1, V2, etc. Vk plus 1, etc. Vn. But what happens is, since this is in W itself, it is a linear combination of V1, V2, etc. Vk only. The coefficients of Vk plus 1, Vn, etc. will be 0. And you have this up to Tvk equal to and for the rest of it, what you have is T Vk plus 1. There is no guarantee that it goes into V1. It goes all over V. We have no idea at all. Therefore, it is in general equal to A1 K plus 1 K plus 1 and so on. Tvn equal to Kn Vk plus K plus 1 N K plus 1 Vn. Now, what is the matrix representation for T? The matrix representation for T with respect to this order basis is then given by multipolar, which breaks up in a nice way. What is it? K1 zeros A1K 2K 3K. This whole block is 0. This is 0. Then you have the usual thing, that is A1 K plus 1 2k plus 2 a k plus. Then etc. n, and then you have one n a two n a two n etc. a k plus 1 a n a k plus 1 n a. This is the structure of this. Now you see that under the assumption that W is invariant under T, we get a certain part of the matrix representation filled with zero elements. It's an advantage. It brings some advantage. More now if we assume or V equal to W plus W theta with PW the matrix represents, see, we can choose an ordered basis for W. You can choose an ordered basis for W tilde, and suppose because under this assumption that, okay, we assume this is so, then you see that you can construct a basis for V as the direct sum of W and W tilde. And W is invariant under T, W tilde is invariant under T. These are the assumptions that we make. Then choose a basis V K median where is a basis for W we are taking dimension of K then this is the scenario. In that case you can easily work out the representation for T with respect to this ordered basis. In that case, what happens is this T B will be of this form. This is a K by K matrix. This is a N minus K. So our task is this. if you can resolve V into the sum of invariant subspaces, then we can get the representation of T with respect to a ordered basis suitably introduced into this form. That means more and more zeros will start coming in the representation. And in fact, in the diagonal form, what is happening is that it exactly breaks down into 1 by 1 matrices. And there will be non-zero entry only along the diagonal, elsewhere everything will be 0. Okay? So that's the beauty of this whole thing. Therefore, we observe that the problem of getting transparent simple reduces to finding suitable invariant subspace. So we end with a question: how to find this is the central question that we are now going to address. How do we hit upon these suitable invariant subspaces? And we have seen that eigenfunctions, finding eigenvalues and eigenfunctions is one method. Okay? And there are situations where you may not have enough eigenvectors spanning the whole space, and that is where all the problem arises, the new problem arises. Otherwise, we have completely solved the problem. Okay? So this is the final question that I raise in this lecture, namely how to find the invariant subspaces. This will be the theme for further development. Okay? Thank you very much.